Hi folks, it's Andrew Kilpatrick here, and I want to tell you about the D100 Quad VCA. This is a little Eurorack module that I made a few summers ago. Basically, I wanted to build some modules for my Eurorack system, not ones that I make commercially, but I make a few Eurorack modules under the Kilpatrick Audio brand. But these are things that I just needed in my system and didn't really feel like doing as full products, so I sort of just DIY'd them. So this is a quad voltage controlled amplifier. It has a level control, so you can just turn it up and down. It has two CV inputs that mix the CV signals together, so you can have like amplitude modulation plus the main envelope signal, let's say, and then each channel has an input and an output. And that's basically the idea. These use the SSM2164 VCA from Analog Devices, which unfortunately is no longer available. But there's a substitute model called the V2164 made by Cool Audio, and you can still buy that if you look online. Okay, here's the schematic for D100 Quad VCA. Basically, we have four sections that are the same. These are shown horizontally like this. And then we have some stuff down here. This is bypass capacitors for the op amps and the VCA chip. And then some filtering here for the power. And then also the power input connector. There's some diodes to prevent damage to the circuit if the connector is plugged in wrong and things are backwards. So essentially we have four copies of the same circuit. The left-hand side, these parts here, are all to do with the CV inputs and CV processing. And this side here is the audio processing. So let's take a look at one section here. Basically what we have is we have an inverting op-amp circuit. We've got this 33K resistor here. We have another 33K resistor across the feedback of U2. And that essentially would make an inverting amplifier with a gain of -1. This C2 here is used to limit the high frequency response. Because we only have a gain of -1 here, the bandwidth of this circuit otherwise would be rather high, and we want to prevent any sort of high frequency noise or RF or something from getting amplified here. Essentially, we think of this like an inverting amplifier, but then we stick the VCA part in the middle here between this normal input resistor and the actual op amp itself. And what this does is this is a current in, current out type device. So essentially what will happen is a voltage on this pin will adjust the amount of current that can flow through this circuit. So just to point out, we've got these extra resistors on the input here. This is just sort of a way to provide a bit of attenuation on the input. And also, you can use little networks like this to basically attenuate plus set some sort of input impedance that you want depending on what you're trying to do. One other point here, the output usually comes out of these kinds of circuits through about a 1K resistor. This serves two purposes. One purpose is that it prevents any sort of short circuit on the cables or things outside here from damaging the circuit or causing excessive current flow. It also makes these kinds of circuits more stable. In the case of you having a long cable, cables are capacitive. If you just have a long cable connected directly to the output of an op amp, it can sometimes, the extra capacitance can sometimes upset the feedback network here and cause some oscillations and things like that. So just use a 1K resistor on most synth circuits, and in most cases that works just fine. This R57 here, 100K resistor, this is used to ensure that the output is terminated when the power to the circuit is off. Okay, so our signal comes in here, we've got an inverting amplifier, it feeds to the output, and then the magical business of doing the VCA part is this part here, the SSM2164. This is a quad chip, that's why there's four copies of this circuit. All four are done in one IC. So essentially we got the current going in and out here, and the amount of current that comes out versus what's going in is determined by this pin here. This is the control voltage input pin. So here's the deal. If the control voltage is at 0, then this just passes the current through at the same amount. So essentially what we would have is we would have a gain of 0 dB. Forget about the inversion here, because these kinds of circuits will invert the signal, but the gain is 0. There's no gain, there's no attenuation. As we start to raise this input signal voltage here, the gain will go down, which means we're adding attenuation essentially, and the amount of attenuation will go up or the gain will go down by 33 or 1 dB for every 33 millivolts that we increase this signal above 0 volts. So if you think about it, 33 millivolts, let's say, times, let's say, what's the range that we want? We want about 90 dB, maybe a little more than 90 dB for the full range of signals. So if we want to go from, let's say, no attenuation to essentially muted, which would be sort of like 90 dB, maybe a little bit more, that's about a 3-volt range of control that we want here. If you take this voltage negative, the VCA will actually add gain, and I think the range is up to about 20 dB of gain that it can add. So yeah, you get a little bit of added gain, and you get attenuation all the way up to, I think, over 100 dB is the maximum attenuation. So that's perfect for our case. And another good thing about it is that the response is logarithmic, in that we have an equal number of dBs per volt. So we don't have to make an exponential converter or any sort of fancy schmancy stuff like that. All we have to do is send in a linear voltage that goes from 0 to, let's say, 3 volts, and the amplitude of the output signal will drop according to a logarithmic scale from no attenuation to essentially muted. Okay, so that's pretty good. We know we need to have a signal from, let's say, 0 to 3 volts to do the attenuation that we want. Over here, we have exactly the circuit that we need to do that, of course. We have 2 CV inputs per channel, CV A and B. This lets you put an envelope signal into one and, let's say, an amplitude modulation signal into the other one, or something like that. And then we also have a pot. The front panel pot sets the offset, and it also lets you open and close the VCA when there's no input signal. Those 3 inputs go into a summing amplifier. This is an inverting amplifier, just like the one on the other side. The summing amplifier basically adds the 3 signals, inverts them, and puts them out to the output here. We've got a 1K resistor here, same as over here. Some sort of resistance in the output of a circuit before it feeds into something else is generally a good idea. This serves another purpose as well, which I'll explain in a moment. Now you'll notice R22 here is a lower value than these input resistors, so the gain of this circuit is actually going to be a little bit less than 1. Or -1, as the case may be, because what we really want is we want something like 0 to 5 volt range or so, or to give us the full range on the VCA. And we know that we don't really need much more than about 3 volts range to cover the entire dynamic range of audio. So to feed a 5 volt signal in here, pretty much half the range would be wasted. So, you know, everything would turn down really quickly, and then there would be a whole bunch of leftover range in the signal that nothing would happen. So to fix that problem, we just reduce the gain a little bit. You could do this another way. You could put a resistor divider out here or something like that. But this seemed like a simple way, and it seems to work pretty well. So if we feed a signal here from 0 to 5 volts, this will make a signal that goes from 0 to -5 volts. Now, we already know that we don't really want that over here, and that's where this pot comes in. You basically set this pot so that the signal is muted. That would mean that there's about 3 volts on here. And then you plug your input signal in, and if you drive your input signal higher as the voltage here rises, the voltage here will go down, but by a smaller amount because the gain is lower than 1. And that will give us the range that we want. And if the absolute range of the signal is not quite right, we just adjust this pot to get the correct response that we want. Now, there's a little diode here. This is a Schottky diode, D1. The purpose of this diode is to make sure that the signal here doesn't go very much below 0 volts. Because we know that if we go below 0 volts, this will start to add gain. And we don't really want that, because in a synthesizer, we're already feeding a pretty large signal in here, maybe 5 volts or 10 volts peak to peak, a 5 volt peak signal. And if we were to add tons and tons of gain, this would eventually run out of headroom and then we would get clipping. So we don't really want that. So I just put this diode here. That means that if the signal goes below about negative 0.2 volts or so, 200 millivolts, then this diode will start to turn on and it will limit the output from going any more negative. So that's basically it. It's pretty simple to build it. Go to dintree.com if you want to download this schematic, and you can look at pictures of the board and go and build your own. Thanks a lot.